Good morning, everyone. There's a lot of you. Although that doesn't look like a lot, I think that's a lot of you given that we're in a city with such an excellent nightlife. I'm Matko Wozniak. I'm one of the co-organizers of the workshop, and it's my privilege to welcome you all for the first workshop on neural abstract machines and program induction. Underneath, you can see the URL where you can find all the information about the workshop. So a few words about our motivation. We kind of saw recently a surge of interest in code induction, differentiable computable machines, differentiable abstract structures, and many other approaches which either wanted to induce code or combine code and learnable models. So knowing that there's been a lot of work in different areas like program synthesis, probabilistic programming, deep learning, and reinforcement learning, you kind of thought that we would all benefit from having people from different backgrounds, people from different views on a similar matter coming here and kind of discussing the future, discussing common challenges and lessons learned from your background. So the goal of this workshop is to kind of bring us together to exchange ideas and well, see the exciting area of program induction and differentiable computation. So in order to jumpstart the discussion, we have an amazing lineup of speakers, and we divided them up into 4 different sessions. So immediately after these opening remarks, we're going to see Stephen Muggleton from Imperial College London, Daniel Tarlow from Microsoft Research in Cambridge, and Charles Sutton from University of Edinburgh. Then, following the first coffee break, we'll listen to Donna Prekup from McGill University, Rob Fergus from Facebook AI Research and New York University, and Percy Liang from Stanford. Then we're going to have a little lunch break for 1.5 hours, after which we're going to have the third session with Martin Weche from Deep Code and ETH Zurich, and Ed Grafestedt from DeepMind. The poster session will overlap with the coffee session, so be aware of that. It's going to last for an hour, but we're lucky enough to have DeepMind as our sponsor, so we're going to have some refreshments over here, and I think it's a good thing to kind of talk about posters over a bit of sangria, so that helps. After the poster session, we're going to have the final session with Jürgen Schmidhuber from ITZIA in Switzerland, Joshua Tenenbaum and Kevin Ellis from MIT, and Alex Graves from Google DeepMind. The last event that we prepared is the debate between Percy Liang, Jürgen Schmidhuber, Joshua Tenenbaum, and Martin Weche, moderated by Nana de Freitas, after which we will give the Best Paper Award and do the closing remarks. So a few words on the accepted posters. We have 5 accepted papers and 9 extended abstracts, all of which you're going to see posters on, I presume, on the left wall from my point of view. You can see all the accepted papers and the extended abstracts on the workshop webpage, and all the accepted papers were put in archives, so they're there to stay. So once again, be aware that the poster session will be overlapping, and there will be refreshments. We're grateful to our sponsors, Google DeepMind and Bloomsbury AI. As I said, Google DeepMind will provide refreshments, and Bloomsbury AI will provide the Best Paper Award. We also wanted to thank all the following people who helped us greatly with reviewing, because they helped us select the papers, and they also gave valuable feedback to all the authors. So Alex Gaunt, Andrew McCollum, Antoine Board, Armand Julien, Charles Bousser, Ian Han Lin, Greg Wayne, Jacob Andreas, Jason Weston, Lukas Kaiser, Luke Zettelmoyer, Mark Rockschmidt, Samir Singh, and Sumit Chopra. And once again, a very warm welcome to everyone from the full organizing committee. So there's me, Matko Wozniak, Tim Rockdashel, and Sebastian Riedel from UCL, Arvind Nilakantan from UMass Amherst, and Nanda de Freitas, Tejas Kulkarni, and Scott Reed from Google DeepMind. So sadly, not all of us are here. So Arvind, Sebastian, and Scott weren't able to be here, but all of the other ones are here, and you can give us a word later on. So I think this is all from me for now, and without any further ado, let's start with the first session. Thank you.
Right, good morning, everyone. It's my great pleasure to open the first session, and we have Stephen Muggleton from Imperial College to give us first.
Okay, so great to be here. From the title, this is supposed to be a provocative title about the notion of abstraction. Okay, so since we're talking about program induction here, it's worth looking at this particular term abstraction because code abstraction is a kind of standard of software engineering. The idea being in code abstraction that you have a piece of code which gives the program writer a kind of abstract view of more complex code underneath, but with a very simple interface, i.e. it hides all of the details and allows the programmer to concentrate on particular issues. Okay, so abstraction is also a kind of more general idea to do with human thought and the way that people turn notions like rooms or people or individuals or tables, etc., into words and then apply those words in different uses. So we can even think of numbers as particular abstractions that are applied as both as individual objects and as functions when they're used to talk about repetition. Okay, so the question is this a useful idea? And in the context that we're looking at here of program induction in various different formalisms, is abstraction useful? So my background is, I'm coming from inductive logic programming, which is a field that I helped found 25 years ago. So I'm going to be talking in that context about the learning of logic programs from examples. The work that I'm going to be describing here is very recent, so really starting from about 2013 onwards, and I hope to give you a positive answer to the question in the title. Okay, just to kick off straight into the issue, suppose that you were trying to train a robot to serve the coffees outside, and you decided you were going to provide pairs where you have an initial state of the world and a final state of the world. You give descriptions of those in the state description. You give a number of examples, and the intention is that a program should be generated which will do the transformation that you want. So in the initial state here, the robot waiter is holding some coffee and tea on a tray. There are various different cups that are the wrong way up, and they're labeled with either a T or a C. The robot doesn't know until it comes to an individual one whether it's going to have a T or a C on it. And in the final state, the ones with a T on are all supposed to have tea in them, and the ones with a C on are all supposed to have coffee. Okay? So the approach that we've been developing in my group recently is a subset of inductive logic programming called meta-interpretive learning. And I'll explain why that name is given. But first of all, I'll show you what meta-interpretive learning does in this particular case. Okay? So in the 2015 paper in Machine Learning Journal, what we did is we introduced a new technique that did something called predicate invention. That is, allow the introduction of auxiliary predicates into definitions in a logic program. Our examples, as you see, are pairs. So each of these predicates that are used is a dyadic predicate in logical terms. It's got an input and an output. The initial state here, for instance, in the first rule is AB, and that should be read as carry out the transformation F by doing an F3 to AB and check if you're at end at B. Okay, so this is a rule that's automatically generated from an example. All of these are generated. In the process of doing this, F3 is constructed as an invented predicate. So F3 basically does an F2 and then move right. F2 does a turn cup over and then does F1. F1 checks whether a T is wanted at that position and pours a T. Otherwise, F1 tests whether there's a copy that's wanted and pours copy. Okay? So this is learned from typically 3 examples of the kind that I've shown you, with a state description given for each one. Okay? And this level of this size of program is unusual for being able to build from that number of examples. It takes something like 30 seconds in order to generate this, because there's a search, as you might imagine, through space. But that's on the same laptop I'm showing you this on. Okay, so that shows you how, for instance, recursion is learned in this case. The talk that I'm going to give you, I'm going to show you an advance that was made in our paper this year at ICHCAI 16, in which the previous program was allowed to be expressed in a more compact way by using a combination of what we call abstraction and invention. Okay, so abstraction here is the code abstraction idea that I gave you. So we have an abstraction, various different abstractions, which are essentially program constructs that have been given in second-order logic. Okay, so these constructs include until. You might also have other functions like map and so on. And the point of the code abstractions is that they allow you to avoid the search through the space of recursions by giving you a kind of general construct for doing recursion without having to do it. You just need to fill in the slots. Okay, so the until abstraction takes the arguments that are going to be transformed, the A to B, but in addition, it takes a condition, which is the condition which the loop will continue until that condition holds, and an action. Okay, so the action here, so the condition is the same at end, which is a primitive predicate that was given in the previous program, and F3 is invented. Okay, so when an abstraction is fired up, then it either uses things that you already have in background knowledge, predefined definitions, or it invents something if necessary. Either invents the condition that's necessary for making everything work, or the action that will be necessary. In this case, F3, the action is created, and the action does an F2 and then move right, where the F2 turns a cup over, does F1, and then the F1 uses another abstraction, which is if then else, which does a test on once T, and in the case it's true, it pours T and otherwise pours coffee. Okay, so the effect of this you should see in terms of the fact that this is a shorter program. There's only 4 clauses here with respect to 6 clauses here, and that difference, because this is a search which requires exponential amounts of time, means that, in fact, this program is found in about 2 seconds. Okay? So we've got a big speed up in terms of the search, and we've got a similar, actually possibly easier to read version of the program. And as I say, the abstractions work off a set of defined predicates, like until, while, if then else, map, etc. They fire off inventions, in this case F3, F2, and F1, which may be fired off recursively or in a nested way to decompose the problem down. And the inventions themselves fire off further abstractions. So out of F1, we get if then else fired off as another invention step that needs to be made to introduce the next predicate. Okay, so here is what's given for the abstractions in that case. So until simply does a condition, and if that doesn't succeed, then it does a do on the do predicate that's given. The abstraction for this, so that's the higher order definition. The abstraction for it is this one here, which is basically a meta rule, that is a higher order template that's used for constructing this abstraction. And the invention, in the case that I showed you, are rules of this kind, which are made from meta rules. Okay, so I've mentioned something new here, which is absolutely crucial in the approach, which is the idea of meta rules. Now, meta rules are second-order logic rules, which, if you like, they form the printing press vocabulary for creating these programs. They're templates themselves, but they have predicates which need to be filled in, and the filling in process either uses predicate symbols that exist or introduces new ones. So in this case, the first three of these are very standard meta rules that we've used. We've proved properties about the completeness of these with respect to search space. We know that, for instance, we can build any Turing machine program using only two of those meta rules, in fact. The last two of these are added for the purpose of abstraction. These are the kind of higher order variants of these which allow arguments which themselves are predicates in the rules that are constructed. The the last column here, these are various constraints that are tested, and the purpose of these constraints is to guarantee things about the computation. So you can prove within the calculus that you'll get guaranteed termination both of the learning and of the learned program, and you can even prove time complexity properties of the algorithm based on these constraints. So the constraints are all based on the idea of an ordering over symbols, and this idea goes back to things that were done in data log within logic programming, and further back to the proof of convergence of rewrite rules. Okay, so this is an idea which is very rich and allows you powerful properties to be tested as you build and construct the program. So I still haven't told you how the program is constructed, what the learning algorithm is, and you might expect the reason I'm not telling you that is because it's thousands of lines of code. In fact, the reason this is called meta-interpretive learning is because it's based around a variant of a meta-interpreter, which is basically a prologue, a piece of prologue that interprets prologue. Okay, so it's like Prologue's version of a universal Turing machine. This program taken a prologue program will produce the behavior of that prologue program. So it's an interpreter, but with a twist. Okay, this interpreter will actually generate programs in the case that it isn't able to complete the proofs of particular examples. And it does so in a recursive way. Okay, so with an empty set of examples, it won't change anything. In the second rule, if you've got a set of examples, then it'll try to prove those if it can from auxiliary predicates, including higher order predicates. If it can't do that, then it'll move on to choosing a meta rule. So I showed you some of those meta rules. It will build substitutions for those, and with those new substitutions, it'll save them in a substitution base, which will then be used further on. So it's building its background knowledge as it goes along, including the inventions. It does an abduction, which stores that clause that's been built, and then it proves the body. So it recursively constructs the entire program. The meta-interpreter is the heart of the entire learning process. And by recursion, it builds and proves the entire program. Okay? So it's both a prover. If there's nothing, if no extra clauses are needed to complete the program, this is a standard theorem prover, if you like. Well, not standard, it's a second-order theorem prover. If you need extra bits, it'll build them as ground substitutions of meta rules. And that last bit is important. We're only doing ground abductive reasoning, and yet we're getting the effect of building programs that have variables that allow generalization. Okay, so this system is called Metagol. It's available, the code is all available for you to try together with examples on GitHub. Okay, so the results, so we carried this out as experiments, and what we found is that not only did you get big increases in speed just by the use of these very general higher order abstractions, okay, so we more than doubled the speed in every case when learning up to 5 examples, but actually we get better convergence, we get better predictive accuracy on unseen data, okay, so we get a double hit, right, and these are not trivial differences in predictive accuracy, as you can see, and the reason is because we've squeezed the hypothesis space. By making the hypothesis space smaller, we know from general results from the computational learning theory, like the Bloomer bound, that we're almost inevitably will get better predictive accuracy. So abstraction gives you a double hit, faster learning and much higher predictive accuracy. Okay, meaning that we can effectively learn, in this case, up to 100% accuracy in 3 examples, as you see. So, this is just a very, very quick and brief introduction into a long field of inductive logic programming. I'm going to move on now to something which I'm slightly hesitant about doing for most of the reasons that I don't normally give demonstrations in the middle of a talk like this because things can go wrong. First of all, I have to give various different disclaimers, right? So I did this in the last few days for the purposes of this workshop, and I wanted to show something that I could easily just do with normal printing and so on, so don't expect fancy graphics, okay? So the idea is the following, right? So this is the second time I came to NIPS, and so I'm aware that this community is interested in going from sort of pixel array descriptions through to some form of learning. So I thought that's an interesting challenge for inductive logic programming, so I thought I'd have a go. And what I thought I would do is before I played around with PostScript, I don't know if any of you remember PostScript. It's basically generates pictures, and it used to be the standard language for printers. It pretty much is still. You can make a version of PostScript in Prolog. In fact, surprisingly, standard PostScript interpreters on printers are written in, they contain a Prolog interpreter which runs them. Okay, so what I've done here, though, I've simplified PostScript down to 3 basic commands: draw, turn 90 degrees clockwise, turn anti-clockwise by 90 degrees, and as it's doing this, it's doing it within an image array. Okay, so what I was interested in is, first of all, doing one-shot learning of simple drawings. Okay, so the idea is this, with the draftsman's assistant, the draftsman is supposed to do a drawing of some kind, like drawing a letter L, and then the observer, or the learner, is supposed to propose a program that does what they've just done, okay? That has the same effect. And then we'd go on to use some kind of higher order abstractions In this case, the abstractions are numbers. Okay, so I said you could have if, then, else, and while, and so on. But if you think about the nature of an abstraction, all it needs is some kind of a symbol, and we could call the numbers whatever you like, but the effect of a number is to allow repetition to the degree of that number. Okay, so with the number 2, you're going to get, if you've got L as an underlying thing that's been learned, and you were shown 2 L's, you should get 2 applied to L should give you 2 L's, and 3 applied to L, and so on. So I'm going to do, in the demo, what I'm going to do is show you how this works incrementally. So although each bit that we do the learning of is a fairly small program, by the end of the demo we've actually built quite a big program, maybe only 10 lines or so, but in Prolog terms that expresses a reasonably big program. Okay, so let me see if I can do this. Right, so I'm going to call up Prolog, which is a standard Prolog interpreter. Can everybody see this at the back? I hope so, because I can't make it much bigger than this. Well, nobody says otherwise, so I'm going to consult an input file called count. And what I've done is sorry?
Can you make it a bit bigger?
I can't make the lettering bigger. I don't know how to do that. How do I? Hey. Okay. Great. Thank you. I've learned something. Okay, so we've got. Can you see now? Okay. So I've consulted the input file, and now what I'm going to do is I'm going to. There's a little program that generates a lowercase l. So I'm just going to try and get it to do that. And so the lowercase l is, you can see these 3 lines here. And it generated that, and then it sent the following command over here, or the following example to the learner, which gives the image, the whole image is handled as a variable, and it gets the initial image ranked with the following order of this element. And it's telling you to define a program that does that. Okay? And this is a Prolog program that defines, it takes a fraction of a second to say, okay, LAB, if you do a draw one, A to C, A is the initial starting point, and you do the timeline. Okay, so it's actually done an anti-clockwise 90 turn. Great. Okay, so I'll do something that builds on that. So I'll do a step. Okay, and up in that top left-hand corner, now the capital L, the step was given again in a similar way to the image. Now it's reusing little l. Okay, so instead of step, can be done with little l followed by step 1. Step 1 is a draw 1 followed by a turn right. Okay. So if I now do, let's see, L2. Okay, so L2 tells the drawer to draw 2 of those little L's. Now we're under a turn 90 at the end, so afterwards it does essentially a capital L again. Okay, so if I do L3, any guesses as to what shape is going to turn up? Don't be shy. U, very good. And so if I do S3, okay, so okay, just invented 3. Okay, so it said 3 was 2, which we invented before up there, followed by 1. Okay, so it didn't have to invent the L; it already had that. So it invented the number 2, and it said 2 to beginning with 1 followed by 1, so that shows you the one program composed with one program, and then 3 is 2 followed by 1. Okay, so if we do S of 4, any guesses? Okay, what it does, it's a staircase type thing out with the L's, because those L's, if you remember, turn clockwise at the end. So 4 of those, and all I needed to do was invent number 4, so it does 4 is 2, 2. Okay, so it's got a vocabulary now where it knows how to do things 4 times, it knows how to do lowercase L's, it knows how to do uppercase L's in terms of lowercase L's, it knows how to do 4. Well, why don't we be adventurous and say, okay, do 8 of these. Okay, so it hasn't seen the number 8 before. The learner hasn't seen 8, hasn't seen any of the other numbers, but the drawer is going to draw 8 of them. And take a little bit longer. So it is 8. Now it says, well, 8 is composed of 4. Okay. So in the process of inventing numbers, it's also figured out how to add numbers, if you think about it. So every time it produces a new number, it tells you how to compose it up out of other numbers. So if I do S of 6, which again it hasn't seen 6 before, a repetition of 6, it knows, it finds out it can do that out of 2 and 4. So any of these numbers, it figures out how it can compose them out of other numbers. And that tells you something quite deep about abstraction and about the way that once you have symbols and once you start assigning meaning to those symbols, you very quickly build up a very, very powerful approach which can be fed with very little information to get to the next step, to build bigger and bigger programs, almost without end. If I can just use one of my remaining minutes to show you that you could have invented all of these numbers along the way. So let me show you, surprisingly, you don't need to give even the names of the numbers in order to do this. So if I do YAP and consult count, and S, L, and then do S, let's say 3. Okay, so I'm going to jump straight into 3. It doesn't know about 2. So it says 3 is 1 followed by something that it'll call to invent something called 3, 1. But 3, 1 isn't 3. It's what? Okay, it's 2, right? 3, 1 is 2, so just keep that in mind. And so when I tell it to do 6, it does it in 3 and 3, but if I do get it to do 4, is 3, 1 plus 3, 1. Okay, 3, 1 is an invention, right? It's just had to make something up called 3, 1. We know 3, 1 is 2. Okay? So, and it's now figured out that whatever 3, 1 is, when you add it to itself, you get 4, right? So it had to invent these symbols in order to get this weird form of arithmetic. So I'm out of time. So the question, I think the statement is that since you've got composition, this just follows from the fact that composition follows the rules of arithmetic. But if you wanted to do explicitly add, then could you do that? The answer is yes, but I didn't include that within here. Learning addition as a recursive definition is something that was done I don't know, 25 years ago in ILP. It's not a particularly exciting thing to do. Inventing the numbers as you go along, that's new, okay? How do you neuralize it? Okay. Yeah, so Natalie, you asked two separate questions there. The first one, I have to admit I don't have the answer to that. Okay, it's the more interesting question, which is how do you get a deep integration of these technologies? The second one is how to possibly get a kind of arm's length integration, and that's something that we have looked at, where you separate out a low-level perception level. We're looking at that in a project with Josh Tenenbaum's group at MIT and also at Nanjing University, and what we're calling it is visual induction. Okay, so the idea there is to, or the Euclid program. The idea is to follow Euclid's approach to vision, i.e. If you look at Euclid's elements, he builds up the visual world as a kind of logical system, but he does it on the basis of starting with some primitives, and those primitives are points of interest in the world. So once you've got points, you can develop lines as pairs of points, you can then develop planes, etc., and three-dimensional objects, and so on. And you can include other classical descriptions like circles and ellipses and so on. So we've done that, and we've used neural techniques in order to identify these points of interest, and then on top of that built an algebra which connects everything together and does reasoning at the kind of ILP end. The issue of speed up, I think, is a separate one, and it's something that I think we can take the lead there from the kind of layered learning that's done in modern neural network technology. And we're starting on that, and hopefully we'll have a paper in INCHCAI about that, which is coming up, which is the idea that examples can be broken into pieces, okay? When you break an example like a visual array or a string into pieces, you can learn bits from those pieces, which can then be recombined logically into a composed overall description. And the learning time drops dramatically. We've already seen that from examples that we've seen. And I think it's very reminiscent of convolution neural networks in that respect. But it's a logical version of it. So I don't know if that answers your question.
Well, unfortunately, we're running out of time, but Steve Martin is going to also have to post in the coffee break. So if you have any technical questions in that question, please stop by.
Okay, thank you.
Our next speaker is Daniel Tarlow from Microsoft Research, Cambridge, and I'm very happy that you're here.
Okay, so thanks for coming. Thanks for waking up early on the last day of the conference. I'm going to talk today about a bit more general topic of things that we've been thinking about. I'll use some examples of our recent work, but the basic idea will be, if you're a machine learning person thinking about machine learning problems, then why should you care about this area of neural program induction? And what are the lessons that we can learn by thinking about programs when we're trying to design machine learning models? And this is joint work with a bunch of people in Microsoft Research and elsewhere. Okay, so just to motivate, I like to have in the back of my mind a little household robot or some agent that we imagine doing a whole bunch of different things. And ultimately what we're trying to do is we have this space of tasks, and we're going to collect data about specific tasks. This might be in a reinforcement setup, or it might be in a supervised setup. That's not really important for the purposes here. But the idea is that you're going to get some supervision in different places around this task space. And so we'll collect a lot of data in some places, a little bit of data in some places. And then if you're training a sort of normal machine learning model, what we tend to think of is we tend to think of trying to generalize just to the little areas around this space. You know, you teach a robot how to clean up your table, and it will learn how to clean up your table, but it's not in general going to learn how to clean up any table. So what we would like, what the aim here is we would like at some point for this idea of strong generalization to kick in. And what I mean by this is at some point, you know, a robot is learning how to pick up a bunch of different types of objects, and eventually it just learns how to pick up basically any type of object or any reasonable object. Or, you know, there's other examples with tasks. Maybe you learn how to clean up one room or a bunch of rooms, and then eventually you learn how to clean up all rooms. And we sort of are looking, and I think we're hoping, and this is kind of what's motivating the ideas here, is for some kind of magic or strong, surprisingly strong generalization. So the idea is that we need, if we want to get here, we need diverse data sets, but it would be nice if we didn't have to collect data for every specific little thing that we want our systems to do. And so the question is, how are we going to get there? And what sorts of models should we be looking at? What sort of ideas should we be looking to in order to find this strong generalization? So I'll talk about two topics today, spending most of the time on the first one. And the idea is going to be to take inspiration from source code. So there's this idea in the software engineering community of what they call natural source code. And what this is taken to mean is that if you look at programming languages, they're these very expressive languages where you can write all sorts of things. But if you look at the way that people use programming languages, they tend to use only a restricted subset of the features. They follow very specific patterns when they're using these languages. And so what you get is you get this narrow, sort of like a pragmatic use of programming languages, which is easier for people to think about and also induces some bias over the types of programs that you're going to write. Okay, so let's look a bit more at this. And so the specific interest here is thinking about it in terms of inductive bias that we can put into our machine learning models. So let's take a look at an example here. Suppose I tell you that we want to write a short program to add two arrays A and B, and here I'm taking A and B to be the same length, and they're just a list of digits, for example. I think all of you could probably do this. The details aren't too important, except the idea is that there's a short program here that we could all write down, which was going to work, and we can think about it in terms of adding arrays of length 3 or 4 in our heads when we're writing this. But because we're using the structure of modern programming languages, we're pretty confident that the algorithm that we write down that's going to work on this small example is going to generalize to arbitrary length arrays as we pass it in. Okay? So just to reinforce this point, suppose I told you, let's now write a different program, try to modify this program, keep it relatively short, and make it so that it works on arrays of length 1 through 20, but then it doesn't work on lengths longer than that. Okay? And so you could, of course, expand this out into a bunch of if statements, but if you were trying to write something compact and natural that looked like the types of programs that people tend to write, then I would argue it's really hard, actually, to write something that doesn't generalize in a strong sense. So this is sort of an attempt at formalizing, not formalizing, or at least like saying at a high level of what we're aiming for here. So we say that programming languages are designed to compactly express the computations that people want to perform, and they make it easy for people to reason about complex computations. And so then the question is, how can we take all of this knowledge that's embodied in programming language design and then use this to bias the types of models that we build from a machine learning perspective. Make one note, so there are relationships of what I'm saying here to ideas like Salma induction and Kalmar complexity. The difference here is I'm thinking about the specific details here. So, we're not talking about binary encodings of programs. We're talking about, modern programming languages and the types of programs that people tend to write. So think Python, not like binary encodings of programs. Okay, so I think this is an interesting exercise just to think about what is it about programming languages that that gives this favorable inductive bias, at least in this symbolic setting. So this isn't meant to be an exhaustive list. I just kind of sat down and thought about the different things that, the different assumptions that come in when you think about writing a natural program and trying to write it at a bit of a higher level in terms of ideas that we can then bring over into building machine learning models. So I won't go through all of these, but there's ideas like a lot of the algorithm execution is often invariant to the specific data that comes in. We write an algorithm that says we have blocks of data and we treat this data as just kind of something to be pushed around and manipulated, but we don't actually look at its values in order to decide the structure, but sometimes we do. There's ideas of structured loops and recursion, so we don't write arbitrary go-tos bouncing around, jumping around in our programs. We have specific algorithmic patterns that we think about. There's a lot of compositionality, abstraction, locality, sparsity, etc. And I'll give some concrete examples now. Having said this, I'm not saying that source code is always a favorable inductive bias. And so specifically when we look at perceptual data, if we're trying to write an image classification system, programming languages were not designed to classify images. And if you tried to write a short Python program from the ground up to identify images, I mean, maybe this will work at some point, but I'm skeptical at this point that this is the right way. So what we'd like to do is we'd like to say, okay, not all data should be treated in this way. What we'd really like is we'd like to use neural networks, which we know work well, for perceptual data, and we'd like to combine those with the inductive biases that I've been talking about before. So this is the basic idea. We want to build models that take some ideas from the type of inductive bias that we get from natural source code, and we'd like to combine it with neural networks in order to handle rich data types. There's a ton of work roughly in this area if you're talking about encoding different aspects of this structure that I listed before into machine learning models, so I won't go through it all. I can't fit it all on the same page. But here's sort of a short summary or a short list of recent stuff. Okay, so let's get into the specifics. I want to talk about two specific things in this section. First of all is one example that's a very human, that involves humans in the loop very much. We're just thinking about, at a high level, these inductive biases, and then building a specific model that captures some of them. And then in the second part, I'll talk about doing this more flexibly and trying to move more towards programming languages. Okay, so let's talk about graph algorithms and graph neural networks. So the idea here is that in a lot of cases there is graph structured data, and we're interested in operating in graph structured data. And so let's think about the algorithms that we write as programmers when we're operating on graphs. And so one example here is the Bellman-Ford algorithm. So this will, given an input source vertex and a graph, it will compute the shortest path from the source to all other vertices. And the interesting thing about this algorithm is, again, like I've been talking about before, you give it any input graph and it's going to be correct. Okay, so there's something about the way that we think about graph algorithms, or the way that this is structured, such that we're going to get generalization to any graph that we pass in. Okay, so we won't go through the details too much, but the basic idea is you keep track of some state at each node, and you're going to initialize that somehow, and then you're going to continually iterate over the edges, and then you're going to do some update of a node state based upon the state of the neighbors. Okay? So at a high level, we initialize node representations. We repeatedly apply these update operations where we update the representation of each node as a function of the neighbors. And then at the end, we'll have a step where we can decode a solution from the node representations that we have. So the idea of graph neural networks is to do the same basic thing. We're going to have these 3 steps. We're going to have a step where we initialize the representation of every node in a graph. There's going to be a repeated propagation of node representations, where nodes representations get updated as a function of their neighbors. And then at the end, there's going to be a decoding step where you have a representation of each node, and you're going to use that to make some sort of prediction. And the idea here is, like we like in neural networks, this is all going to be differentiable, and we're going to train the whole thing end to end. Okay, so a little bit more detail here. There's a few papers here. Graph neural networks first came out, I think in 2005 is the first reference I know of there, by Gori and Moncardini and Scarcelli. There's a couple papers there, and then we have a paper in last year's iClear that adds some modifications here. It modernizes it using gated recurrent units and modern practices around neural networks, and limits some of the restrictions of the original graph neural network model. But this is just in a bit more detail. The idea is that you're going to get as input a graph. So here in the top left, we have a graph. You're going to have edges, which are labeled with an edge type, which is denoted by color here. So there's gray edges and there's black edges. And then what you're going to do is you're going to have what is basically a recurrent step, but each edge type is, you can think of as a little neural network that's going to share parameters. And then you're going to pass node representations across edges, and the transformation that is applied across an edge is determined by the type of the edge. And then you unroll this whole thing into a big recurrent propagation, and you get back a graph neural network. So I won't go into more details here, but I'll refer you to the papers to see exactly how this works. So let's look at why this is an interesting idea, and let's look at a simple reasoning task. So one of the baby AI tasks from Facebook AI research. So here, I've taken one of the tasks, but there's an option in the data generation to produce data in a symbolic format. So instead of having this natural language rendering, you can just get the data rendered out as basically a graph. So each line here has a node, a relation, and then a node. Okay, so here we say D is A, B is E, A has sphere F, and eventually at the bottom here, what we want to know is, does B have fear of H, or is B afraid of H? Okay, so we want to say, given all of these facts, we want to answer this simple question at the end. So the simple way of representing this problem, if you aren't really thinking about it, or if you just want to say, I want to use a neural network, then what you can do is you can pass this into a recurrent neural network, LSTM, whatever your favorite recurrent architecture is, and you would just encode it as a sequence. So we might insert, we could say D is A, and then we have an end of line symbol, and then we have another fact, and we have another fact, and we have another fact, and then at the end we'll get a question that says eval whether B has sphere of H, and then what we want out at the end is yes, in this case. Okay, so you can see how you can train this. The question, though, is to think about what generalization properties this is going to have. And I argue that representing the problem this way is going to be inferior to representing it as its native graph structure. Okay, so what would the alternative look like? Oh, so just one note here is names are going to be an issue, so if you're concerned about that, we can just normalize the names and say, we'll just rename everything to have the first node be named node 0, the second node named node 1, etc. But now let's look at how you would represent it as a graph. So as a graph structure, you can take all of these relationships and you can construct a graph out of them in the natural way. So each node here corresponds to one of the entities, and each edge corresponds to one of the relationships. And I've marked in green and blue the special nodes that we're concerned about. So B is the first argument of the question, and H is the second argument of the question. And we want to know, does B have a fear of H? And represented this way, you can see that it becomes clear graphically what the sort of relationship that we're trying to determine is. What we want to know is, basically in this problem, the only way that something can have a fear is if you follow a sort of a transitivity relation that says, B is an E and E has a fear of H, or B is an E B is something else, and something else has a fear of H. And so you can see that certain types of relationships like transitivity can become easy to encode in this representation. And then also the question can be answered based upon a local region of the graph. So if you had a whole bunch of other distracting statements, those would just naturally get ignored in this representation, or their influence would only come through propagation across a long distance of the graph. Okay, so the properties of this, I guess I've already just said these, so I'll skip through. The main limitation, of course, of this graph structured representation is that it's not always easy to convert our data into a graph structure format. So if you were really working on raw natural language, then mapping natural language to a graph structured representation is a challenge. There's a recent paper submitted to iClear that starts to look at this, but this is definitely a problem with these models at this point. So let me just show you some results. So we took some of the baby tasks where they were particularly well suited to a graph structured representation, so there wasn't a temporal component that we needed to worry about. There weren't higher order relationships so that we would have to have hyper edges. It was just the simple problems. And what we see here is the recurrent neural network and the LSTM models do much worse. So what we have here is we have the performance, and then in parentheses the number of examples that you needed to see in order to achieve this performance. And so what you see is with just 50 examples, which is the smallest that we tried, the graph structured representation here basically does get 100% on all of the tasks, whereas even with 1,000 examples, the recurrent neural network problems struggle with this. And then in our iClear paper, we also extend graph neural networks to output sequences, so you can do things like not just make a single prediction, but you can make a sequence of predictions, like predict the shortest path in a graph, or find an Eulerian circuit. And again, if you compare how the graph structured representation does to the RNN representation, then you get much better performance from the graph structured representation. So the basic takeaway here is that when a problem is well represented as a simple graph, then the graph neural network representation gives a more accurate model and allows us to generalize more strongly from less data. Okay, so let's move on to the second thing. So this was a very specific algorithmic template. Let me go quickly into the more general version here. So the idea here is we set this graph algorithm template. Now what if we want to not only, what if we want to learn this template as well? And so the idea is going to be to build upon differentiable interpreters to try to learn the algorithmic template as well. So let me just go quickly about what a differentiable interpreter is. So an interpreter, of course, tells you how to execute a program. Given a representation of a program and an input, it will tell you how to produce the output. So here's a very simple differentiable interpreter. What we're going to say is there's two registers, register 0, register 1, and then the question marks are things that we need to fill in. So we're going to be interested in figuring these out via the learning algorithm. But we're just going to say that there's an array of instructions. We're going to choose one element of that array. We're going to apply it to the input, and then we're going to store it in one of the registers, and then we're going to return one of the registers. So you can think of this, so each of these are, each of the orange question marks are discrete variables which represent a program. And so you can see that if you were able to fill in these orange variables, then this would give us a program back. So you can think of this as a graphical model where what we have here are the orange are the parameters that we're trying to infer, and then we have this series of deterministic operations that tell us how to map from the input to the output given a set of program variables. So the way that we're going to make a differentiable interpreter is we're going to start by letting all of these orange program variables, or params as we call them, be categorical distributions. So we're going to initialize them randomly. They're going to have some trainable parameters behind them, and then we're going to have a distribution over their values. So it's like, which instruction do we apply first? Which register do we store the result in? And then you're going to lift all of the operations to be differentiable. You're going to observe the inputs and the outputs, and then we're going to train this by maximizing the probability of the outputs given the inputs as a function of the parameters here. And we can do this with gradient descent. So there's details here of how to lift the function approximations. This is used very commonly across neural Turing machines, across stacked RNNs, across many of the models in this space. There's also a bunch of related work like differentiable forth and adaptive neural computation or other papers here. There's going to be a poster where you can see more details of how these things actually work, and so I encourage you to go there. And so what we've done here is we're going to say, let's take differentiable interpreters and let's extend them to handle perceptual data. So we have a ICLR submission on this topic. So this is just a simple example to show how this works. What we're trying to do here is we're trying to take a tape and we're trying to learn how to classify dinosaurs just from count supervision. So at the top here, you're given a sequence of images and you're told there's 3 dinosaurs in there. And then what we have is we have this language for defining models where what we're going to be able to do is we're going to define discrete functions. So this is like defining a differentiable interpreter. But we're also going to have operations that allow you to define neural networks. So this is defining a function called isDinosaur, but we're not supplying an implementation. We're just saying it's going to be a neural network that is to be trained. And then what you can do, then there's other program variables to infer. And then down here at the bottom, we can make function calls using this function that is a neural network just as usual. And then at the end, we'll observe the total counts, and then we're going to train this whole thing end to end. Okay? And so then what we're going to do is we're going to jointly be learning the program representation and also the parameters of the neural network that do the classification. So we've applied this in a lifelong learning setup. So there's a series of tasks here. We're going to have basically grids of images or mathematical operators represented as images. And we're going to have a series of simple tasks where we need to induce programs like to add up the top row, the first column, the bottom column, etc. And then what we want at the end, what we're working out towards, is getting a arbitrary length sequence of digits and operators and being able to compute the values there. So the sort of takeaway here that I want to show is that this is resilient to catastrophic forgetting. So we're going to train it in a way where we're going to show it tasks, and the top line here shows how probable it is that we show it different tasks. And notably, we'll start showing it the first task, but then at some point, you can see in the red here, we stop showing it to the first task at all. And the blue line is the performance on the first task as training progresses. And so the notable thing is that even after the last appearance of the first task, performance is still going to improve because all of these different tasks are sharing the same neural network components. Okay? And this is compared to a baseline in the dash where you get this catastrophic forgetting. If you change the task distributions, you lose performance. Okay, I'll just show a curve about strong generalization. Then if we go on to the final task, now we've trained up on all of the previous tasks, and now we're going to give it some training examples of evaluating expressions of length 2, and we're going to train on that, and then we're going to test on much longer expressions, and we get the strong generalization behavior. Okay, I need to move fast, so I'm going to skip ahead. Okay, so I'm going to take 1 more minute if that's okay. So I want to think a bit about this issue of why this mitigates catastrophic forgetting. So the motivation, I think, for what's going on here is, if you look back to like how Jeff Hinton explains mixture of experts in his course slides, what's going on is you have these different components which are chosen with some probability via a gating function. And you have this gating function that controls, if something is picked, then it's used and it gets gradients. If it's not picked, then it's not used and it doesn't get any gradients. And so I think structuring these neural networks within the source code model behaves in a similar way, where you have the outer source code component is deciding which functions or which neural networks you want to use. And if it decides that something is relevant, then this component will get updated, it will get used, and it will get continually updated even as you train on different tasks. But if it doesn't pick it, then it just gets shut off and it gets ignored. So even if you're confused on a later task, if you haven't chosen one of these neural networks, it's not going to get updated, and so you're not going to distract yourself from the training earlier. Okay, so I'm just going to skip to the conclusions now. I can find my mouse. Okay. Yeah, right. I don't know which side it goes off of. Sorry. Okay. I see it, but I don't know where the other screen is. Oh, there it is. Okay, sorry. Okay, so yeah, I'll just leave these up here and here.
It's really nice extraction. So does it able to learn new low-level primitives later on, or is it has to have a fixed size variety of those?
So the question is it able to learn low-level primitives, or does it need to have a fixed size of those? The way we do it, yeah, it's that in each task, we have to introduce the possibility of using new components, and then it can choose not to use those if it doesn't want to, but it doesn't ever explicitly say, I'm in a confused state, I need to invent something new.
Is your source code available somewhere?
This, we've just submitted it, so no, we haven't released it. So the question is, does the approach deal with complex recursion and the introduction of new functions? So the specific answer here for these things that I've shown you is no. It supports loops. We have the last example is a loop, but it's not there's no complicated recursion. The more general answer is casting it within these differentiable interpreters. There's nothing in principle that doesn't, that says we can't define a language, or a source code representation which supports loops and recursion and all of that. So if you go to the poster that we have here, it's not in this perceptual domain, but it's just looking at differentiable interpreters in general. And there we have languages that look like assembly languages that at least support sort of arbitrary structures and different structure control flow. So could you discover new algorithms like quicksort? In principle, yes. In practice is that these differentiable interpreters still don't work very well. I think I'm not convinced that gradient descent is the best way to be searching over program space. So there's a lot of random restarts that you need to do in order to actually have this search perform well. But in principle, there's nothing that prevents us from learning these types of things within this formulation.
Right, let's thank the speaker again. Sorry.
Right, our last speaker for the first session is Charles Sutton from the University of Edinburgh.
Let me check my email. If you'd like to reply to anything, please let me know. Okay, thank you all. It's great to talk to you. Before I start, I'm doing an experiment now, and the experiment is there is a companion website to the talk. So that'll have my slides, links to the papers, everything else. So feel free to go there, spend the first 5 minutes of my talk reading all my slides, and then the next 20 minutes just checking your email. Job done. So what I'm going to talk about is some first attempts at using neural networks to to learn the semantics of real computer programs. So it turns out, and we'll come at that from kind of several different directions. So the way that I became interested in this idea of neural networks and program induction was in a particular way. So I actually wasn't trying to think about the problem of artificial intelligence. I wasn't trying to think about building a new type of robot. You know, I thought there was an opportunity to do, shall we say, stuff that works. And, you know, in particular, the opportunity that I saw was, or that a number of people saw a few years ago, was with all of the amazing amount of professional quality source code that is on places like Bitbucket and GitHub, that there's an opportunity to learn patterns that characterize good software. Why would we expect that to be the case? Well, if you think about, you know, we write source code in something called a programming language. And, you know, the term language is a metaphor, and it's a really interesting metaphor, because as we tell all of our undergraduate students, when we're teaching them computer science, you know, they're always writing code, not just for themselves, not just for the computer to execute, but also for themselves and others to read later, to understand what the algorithm does. So another way of saying that is that source code is a means of human communication. Hopefully it's not the only means of human communication that you have, although for some of us I'm not so sure. But there is an opportunity for applying some of the methods that have been so successful for natural language text and trying to use them to build new tools for programming language text. So there's a number of people in the past 3 or 4 years, including ourselves, have been working in this direction, building new software engineering and programming language tools. So we've looked at things like finding patterns in how libraries are used. So can I find sequences of methods or syntactic constructs that talk about what's the most typical way to use a particular library? And we'll identify those using various probabilistic methods. We also have some work on summarization. So the first time I go to a new source file in Java, you know, what's the most important stuff that's in it? And we also have some interesting work on learning coding conventions. So can I suggest new local variable names that to somebody who's new to a library, I'm trying to make a patch to it, and can I help them write code that looks more like code that's written by more experienced contributors? But one of the things I find most exciting about this emerging area is that pretty much any task that you do in industrial software development, I think there's an opportunity to create better tools based on finding patterns in large corpora of source code. So I've listed a small number of these on this slide, and I think there are many, many more opportunities. So, but in this talk, you know, this is a workshop, so I don't really want to talk about stuff that works, because that should be in the papers. So instead I want to talk about stuff that doesn't quite work. And so the stuff that I'm going to talk about in particular is, as I said before, we're going to try to build neural network architectures that begin to capture certain aspects of program semantics. The first question you might ask about this is, why on earth would I want to do this? If you want to build AI, well, okay, that's one motivation, that programming languages could be an abstraction there. But even from the perspective of programming languages, where, you know, program semantics is something that can be defined formally, you know, why would you want to view it in a statistical way? So I guess that's something that can be discussed during the panel, but two things that I would suggest is that the connection between the program and the domain is one that at some level is always going to be inherently informal. So that would be a modeling problem just like any other modeling problem we have in data science. And the other reason why you might want to think about statistical models of semantics is because, you know, if you want a more efficient method that deals with the semantics of typical programs, you know, rather than something that has to handle every corner case. So now let me get a little bit more specific. So I'm going to talk about two pieces of work that we've done. The first one that I want to talk about is almost like a summarization problem. So what we want to do is learn to name methods. So if I give you a Java method, like the one that's on the left hand of this slide, what I want to do is predict from what's going on and from the identifiers that are used in that method, you know, what the name of that method should be. Because if I know how to do that, then I know something about what's going on inside the method and what's the connection of the domain. So you can view this as a type of summarization problem, or maybe even a type of translation problem, but it's a very extreme type of summarization problem. Because I'm trying to give you this thing on the right that has, I mean, if I split it up on camel case, maybe 3 or 4 parts to it. So how are we going to do this? I'll say very briefly. So we're going to do a recurrent neural network, a GRU, to generate the name of the method. So I'm going to have, at each sequence position, I'm going to generate one of these parts of the name. So at the top, we call these things subtokens. So I'll output that at each step of the LSTM. But then I want the input to take into account this kind of very long sequence that I'm translating from. So the way we're going to do that is via an attention mechanism, which is has become very popular in machine translation. But it's going to be a special kind of attention mechanism to deal with this kind of large length mismatch between the two sequences. In particular, what we introduce is a convolutional neural network for computing these attention values. So the idea of this network is this is a neural network that will output a distribution over sequence locations in the body of the method. And it will say at each time step, as I'm about to generate a new section of the name, what part of the body of the method is most important for generating this part of the name. And that's what this neural network on your right is trying to do. And what he's doing, what he's doing very briefly is the input nodes that I have on the bottom are the embeddings of the tokens in the body of the method. We'll put this through a few convolutional layers. The reason we'll do this is we want to find position invariant patterns that indicate that some token is semantically important. So if I have something like return blank semicolon, then whatever is in the blank is important to predicting some part of the method name. So I'll put this through a few convolutional layers. Then at this top convolutional layer up here, I'll have something that's dependent on the current state of the output generation. So I'll do an element-wise multiplication with the current state from my generation, from my decoder, from my generation LSTM. So that will allow me to choose different features depending on what state I'm in the output. And then I'll output these things alpha, which is my, my distribution over elements in the input, method body. So that's how one of these convolutional mechanisms works. But in fact, we have 3 of them. The reason that we have 3 of them is that often you'll have methods that introduce new types of subtokens that we haven't seen in the training data. We want to deal with this out of vocabulary problem because that means, because often this happens when a method is talking about something new in the domain. So the way we do that is by having what we call a copy mechanism, which is closely related to pointer networks. So we'll have 3 attention mechanisms. One of them is doing weighted average over the input embeddings. That's these alphas, just like is standard in attention. Then the second vector kappa is another distribution over input locations that's saying which ones is most likely to copy to the output. And then the third one is the scalar lambda that says which one of these should I use. So when I actually predict the next token, I use lambda to do a weighted average of just generating a token from the regular LSTM that's looking at this attention value and from copying things using kappa. So let's see a little bit how well this works. So we took a corpus of real Java projects from GitHub, and we said, given the actual method bodies, how well do I do at predicting the names? So these are F1 and exact match percentages. The F1 is a type of partial match. So if the name of the method is like get value, and I manage to figure out it's a getter, but I say get something else, then I get a 50% for that one. So we compare to TF-IDF, we compare to a sequence-to-sequence model that has feed-forward attention, and having this convolutional attention and the copy mechanism, helps us do a much better job of predicting names of methods. Still probably not good enough that you want to put it in Visual Studio, but there are some kind of really good examples where we find kind of non-trivial patterns that I won't go into for time, but I'm happy to talk about that afterwards. So that's one example in which we're trying to combine ideas of tokens from the body and kind of identifiers, which are telling us stuff about the connection to the domain, to do some type of summarization, which we hope that, that we're learning something about method semantics by doing that. So now I want to talk about something that we have, that we currently have in submission, that is trying to get at semantics more directly. So what we're going to do is we're going to take expressions and we're going to try to map them to continuous vectors. So the goal that we're going to have is, given a polynomial or given a logical expression, I want to map this to a vector in such a way that expressions that are semantically equivalent are assigned to similar locations in this semantic space. So why would I want to do that? So I think if we have an effective method for doing this, I think there's some very interesting opportunities for combining symbolic and statistical reasoning. So, in particular, when you're trying to do symbolic reasoning, it's essentially search, right? If I'm doing theorem proving or if I'm doing static analysis or so on. And, those techniques are very effective, but if you think about, what we do informally as mathematicians, I don't know if I'm a mathematician, but when I was a math student at least, a lot of the work that you try to prove a theorem, it's almost pattern recognition. Right? I see a particular theorem I'm trying to prove. It feels intuitively similar to something that I've proven already, and so I should know something about what lemmas or so on I should use to prove it. So, so if we can use ideas that are more from pattern recognition, which is in some sense where AI is currently succeeding right now, and use them within symbolic reasoning, that's an interesting opportunity. So the way that we're going to get started about this is we're going to focus on trying to predict equivalence. And we're going to assume in the training set that we have access to an oracle in order to generate training data. So that, given two expressions, he will tell me whether they are semantically equivalent. If that was too expensive an operation, we could use something like random testing. Now, it makes sense for this type of problem to use some kind of tree-based method, which is a very famous work from Richard Socher called recursive neural networks, which I'll call TreeNNs to try to avoid acronym overloading. And so this was introduced in natural language processing. And what this is, it's a type of deep network where the structure of the network is based on some input tree. So say I have a parse tree of some natural language sentence, and I, for example, want to predict some class label, like a sentiment label or something like that. So what I'll do is I'll create a neural network whose structure follows that of the tree. At every node in the tree, I'll look at its children, and I'll have a feed-forward network that takes a representation, a continuous vector for each of the children, and maps it to one of the parent. So it seems natural to try to do something like this for this problem, precisely because semantics is compositional, right? So it's kind of hard to this seems like a very, very natural place to start. So that is where it started, but it wasn't quite working for us. And what we were finding with these types of models is that they really tended to be keying in on syntax instead of semantics. So when we looked like in our validation set and we said, okay, what are the nearest neighbors in the semantic space that we've learned, we would find lots of expressions where the surface structure was very similar, even if they were different semantically. So one type of example that happens is if we consider two expressions, so these are polynomials, at the top, which are semantically equivalent, because obviously the right factor is the same. And if we look at what's happening in this tree NN, then we'd see a lot of times what was happening is even if the parent is that we would have kind of a child representation, which are of these semantically equivalent expressions that were still getting different vectors. So we would find one semantic equivalence class that was spread out across the space. So what we wanted to do is to kind of add some more kind of tweaks to this to try to encourage it to bring these two vectors closer together. So what we did is this thing we called EQNet, for EquivalenceNet. So we start with this tree and N model. At each level of the tree and N, what we're doing is we actually have a 2-layer feed-forward network using a resonant type trick. We also do some normalization tricks of the representations. But maybe the most important thing that we did is this thing on the right. And that's trying to do this thing of avoiding this having semantically classes be too spread out. And it's a little bit weird, so let me try to motivate this a little bit. So the motivation was, if you think about symbolic reasoning, so think about what you would do, say, doing unification. You get information that's bidirectional. So if I imagine this very simple line of prologue on the, or syntactically incorrect, perhaps, line of prologue on the slide, if I told you the unification of the variables on the right-hand side, you would know how to bind them on the left-hand side. But similarly, if I told you bindings for the arguments to uncle and parent, you would also know what's going on in brother. So the information is flowing both upwards and downwards. And if you're doing a unification, this propagates automatically, but semantic vectors don't know how to do that. So we're going to try to do that using this thing that we call sub-expression forcing. And if you have a better name for this, please do let me know. So what we're going to do is, is that if we force the network, if we just black out this child on the right that's different, and then we force the network to predict the right child of both of these expressions, given the two on the left, well, then, to minimize his loss on that classification problem, he's going to have to bring these two things closer together. So what we're going to do is we're going to add another term to the objective function that is a denoising autoencoder plus a buffer. And the important thing about that is that the input to this denoising autoencoder is going to be this triplet of representations. It's going to be the parent representation, the child 1, and the child 2. I'm going to autocode all 3 of them because I want to be able to predict any one of them given, or a subset. I mean, we don't take the structure into account when we're doing the denoising, although we could. But given a subset of entries from any one of, from some of them, I want to be able to predict the others. And that's basically the thing. We add this as a regularization term onto a tree and N. We get supervision at the top layer, which is that once we have this oracle that tells us equivalence, we can label equivalence classes arbitrarily. So that's basically the whole model. So let's see how this works. So I'll give you actually before I do that, let me that slide seems to have been very enthusiastic and jumped upwards in my talk. So the way we're going to do evaluation is we have we're going to use synthetic expressions, but we have a fairly large variety of different expressions of Boolean and polynomial expressions with different numbers of variables and different operators that are being used. And so you see for the different types of cases we have the number of equivalence classes that are in the data and the total number of expressions which we generated exhaustively. Now we also created a training test split for this. We do this in a somewhat careful way because we want to measure whether this thing will generalize to new equivalence classes. So we have one test set, this purple one, so each one of these little columns is a different equivalence class in the data, which we know exactly. And we have this purple test set at the top, which is a test set of expressions we haven't seen from equivalence classes that we have. And then we have some orange test cases, which are equivalence classes that we haven't seen. And the way we're going to evaluate this is we're just going to do nearest neighbor. So what we're going to do in particular is we're going to see for a particular number of nearest neighbors k, what percentage of the nearest neighbors are actually in the same equivalence class. Okay, so let's see how this works. So what we have here is the graph on the left is from just generalizing within an equivalence class. Excuse me, I know it sounds like I'm about to die, but I'm really fine. And the graph on the right is from equivalence classes that we haven't seen yet. And we compare to these tree neural networks that don't have this sub-expression forcing and normalization trick. We compare to a neural RNN with a stack. We compare to a standard sequence of GRU, and we compare to TF-IDF. which, the identifier names are completely arbitrary, but TF-IDF can at least check, are you using the same variables or not? And we have the number of nearest neighbors on the bottom and this kind of accuracy on the top. And doing these two things together has a huge impact on performance. You see, even if for equivalence classes that we haven't seen before, so we haven't seen any expression that's equivalent to this, we can still group together expressions from the same equivalence class. So the other thing we could do is this experiment on, which was trying to evaluate whether we're learning a compositional representation. And the way we're going to do that is we say, let's suppose we train on expressions that have very shallow trees, and we test on expressions that have deeper trees, right? If we have a big drop-off in performance, then we're really overfitting to these simple problems. Whereas if we still do pretty well on larger trees, then we must be learning a representation that actually is recursive. See, I'm still making that mistake. That is recursive. And so what we find is, the numbers from the EQNet are, you can see from the scale, it's a little bit harder to do this kind of type of generalization than the other ones, but it's not a huge drop-off in performance that we're seeing. So there is some evidence that we're actually learning a semantic representation that's recursive. So now let me go back to this eager slide. So what the slide was is a low-dimensional visualization of a subset of polynomials from one of these test sets that involve A, B, and C. And actually, it turns out you can interpret the locations of these in the vector. So what you'll see is the ones on the left tend to have a negative coefficient for A. And the ones on the right tend to have a positive coefficient for A. Whereas at the top and the bottom gives you the same thing for minus B and B. And if you put a diagonal line like this, then you see one for C and minus C. So it's kind of like this thing with king minus female equals queen, except, a little bit less exciting, I guess. But, or a little more abstract, at least. Okay, so I'll stop here. So just to summarize, what we've been trying to do is come up with different ways to use neural networks to learn kind of recursive semantics on real programs. I talked about this kind of very practical but difficult function naming problem, and then also on trying to move towards things that are looking at semantic equivalence. So, this notion of equivalence is kind of a very difficult notion. If you get this, you've got everything. So I think looking at kind of weaker notions of program semantics, maybe problems that are interesting on the programming languages side, I think that would be a really interesting direction for future work. Thank you very much. Okay, yeah, okay. So I have two questions. One is, would this convolutional naming method work for a declarative language? Declarative, you said, yeah. And the other one would be, would it work in an adversarial method? So let me see. For a declarative language, I am not sure. I have a sense you would want to do, I'm not sure what the notion of, I guess you would take a snippet, but I'm not sure the notion of naming a snippet, at least in declarative languages that I know. I'm not sure what the analog of the problem is, maybe. So I guess it would be one if you're defining a new relation, and then I get to see what's going on all the left-hand sides. You might be able to adapt this architecture for this, but I'm not sure. In an adversarial setting, I'm pretty sure it wouldn't work. Because it would just be too easy to insert irrelevant things. Yes, that's a good question. So bringing back to a question I introduced earlier, which is why on earth would I want to think about this problem, given that there are good algorithms for unification and they work. So, the idea is not that, the goal is not to have something that is practically a best-in-the-world solver for, any type of equivalence problem. What we are hoping to do is learn things about what principles are necessary to build architectures over logical expressions. And, once we have a better understanding of that, we would hope to be able to do things that would help to guide more complex logical solvers. So I think the long-term vision for doing something that does semantic reasoning would be, I think an interesting vision for that, would be having something that integrates symbolic reasoning with more, I don't use the word fuzzy, more maybe statistical pattern recognition type reasoning. Yeah. So I think there are lots of really interesting opportunities on the software engineering side to help programmers write code that's easier to read and easier to maintain. So, so that was like a little bit like some of the stuff that we've been doing now, about simpler versions of the problems that we've been talking about. So, for example. Just learning to name local variables. So, what you could imagine that moving towards is a type of code review assistant that can say, okay, I'm about to submit some patch to a big software project or to a commercial project or a project on GitHub. Before I send it to an expert programmer to review, can I send it to some statistical system that will tell you, look, I can tell you right off the bat, these three things the program is going to flag, so why don't you just fix them now? And I think that's something that we could, it doesn't exist now, but I think that's something we could actually do. Okay, so I'm not sure I fully understand the question. I'll do my best, and we can talk afterwards. So it sounds like you're getting at the issue that we have a very strong notion of similarity, right? So we've got this binary thing that two expressions are either equivalent or not, and we're not taking into account the fact that two expressions that are not equivalent could still be similar. And that's right, we're not taking this into account right now. I think that would be an interesting thing to do to extend the method. If that wasn't answering your question, we can talk offline.